Good morning, ladies and gentlemen, and welcome to the SAIEE Nuclear Chapter webinar on USNC Micro Modular Reactor, Small Reactor, Big Potential. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. This channel is updated regularly, so please find the registration link to the SAIEE TV in the chat box. Please register, it's free. A certificate of attendance will be issued a few weeks after this webinar once we've received the CPD validation number from EXA. I'd like to introduce you now to our host this morning, Professor David Nichols, who was appointed as the chairperson of the board of the South African Nuclear Energy Corporation, NECSA, in January 2020. Prior to his retirement at the end of December 2018, he was the Chief Nuclear Officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016 and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of WANO's post-Fukushima design review team from 2012 to 2018. Over to you, David. David, you're muted. David, we can't hear you for some reason.
I'm afraid the link is somewhat difficult because I'm in load shedding.
Okay.
Can you hear me now?
Yes, we can. Thank you.
Can you hear me now? Thank you. I will apologize in advance that I am in load shedding, so I think my network link is rather poor. The joys of the lack of nuclear power in the economy. And I will just comment before I introduce Chirag, who is the presenter, is that USNC, which is the organization that is presenting today, is building what you will call a micro modular reactor. And I think everyone's talking nowadays about small modular reactors, and I think it's important to understand that there are increasingly being seen as three groupings of nuclear reactors. One is large reactors, reactors like Coburg, let's say 600 megawatts up to 1,500 megawatts. And those are almost being called classic reactors nowadays, dominated by pressurized water reactors. They're basically always linked to large utilities with large grid systems, exactly like Coburg is in this country. Then there is the small modular reactors, which are really from about 30 megawatts up to 300 megawatts, that kind of range, which are being seen as part of the future, probably in terms of grid systems as well, but on smaller unit sizes, and maybe more suitable for smaller grids. And then what's probably most exciting is these micro modular reactors, which are the ones down at, let's say, 5 to 10 megawatts. In other words, almost at industrial park scale. And they're really interesting because they move nuclear completely out of the regime which it's been for the last 70 years, which is always as a supplier to the grid. So with that, I'd like to introduce Chirag Golkadas. I'm sure I pronounced your name wrong. I apologize in advance, Chirag. He has a master's degree in chemical engineering and is registered as a professional engineer. And his knowledge base covers research, design, construction, commissioning of process and power generation, and technical and commercial structuring in project finance, energy projects. What's interesting is that Chirag is working for USNC, which is a US nuclear company, and I want to say US stands for ultra safe nuclear company. Am I correct, Chirag? That's the correct title?
Yeah, that's correct, David. It's UltraSafe Nuclear Corporation.
It's one of the American startup companies whose engineering team is almost entirely in Pretoria. It is really an outgrowth of the old pebble bed modular reactor project, and a very interesting discussion where it's got its primary customer or partner is Canadian. Its commercial and legal base is the USA, and its technical base is Pretoria. So with that, I'll pass across to Chirag. The floor is yours, and I'm looking forward to this enormously. So the floor.
Perfect. Thank you so much, Prof. Nichols. Really appreciate those kind words of introduction. So good morning, everybody. I'd like to really basically thank the SAIEE for arranging this webinar. Really excited to tell you about UltraSafe Nuclear and our efforts to develop and deploy what's called a micro modular reactor. So I'm going to dive in here, and before I do, I just want to get my pointer set up on this presentation. Minx, David, are you folks able to see my pointer?
Yes, please proceed.
All right, great, perfect. So before I dive into the real exciting bits about nuclear energy, I'd like to digress and focus our attention in a different direction. These classic civilizations were all hailed as superpowers of their time, and for good reason. The Egyptians formulated the basis for modern mathematics and built the pyramids. Greece was the birthplace of democracy, and the Romans gave us early forms of cement. Indeed, all of these societies contributed to innovations that we use in the world today. But there's a common thread with these civilizations, and that common thread is that they did not respond to existential threats. Some say that the Mayans overexhausted their environment to the point that it could not sustain their population. Interstate conflict and inability to unite caused the downfall of the Greeks, and the Vikings suffered from increasingly arid conditions which devastated their ability to produce food. What's interesting to note from this slide is that the average lifespan of known civilizations is 336 years. Since we've started burning fossil fuels in our post-industrial revolution phase, we're at a mere 263 years old. So just some perspective in terms of being able to respond to these existential threats that potentially challenge the social structures. In his 2005 book, Pulitzer Prize-winning author Jared Diamond argues that social collapse is a choice, and I believe that we have, as a global society, a very pressing matter and a choice to make in terms of our future existence. So what does that look like? And what is today's existential threat? And I'm sure you've all guessed it, but it's in fact climate change amongst, let's say, a host of 5 or 6. So I really want to focus on carbon emission trends over the last 50 to 60 years. The Intergovernmental Panel on Climate Change was established in 1988. And in spite of this early start and our knowledge on climate change, we've struggled to wean ourselves off fossil fuel. In fact, we've approximately doubled our CO2 emissions since the establishment of the IPCC. Power generation, industrial heat, and transport remain the critical and the largest emission contributors. And really, this picture does not paint a very good scenario for us in the future. So what does the prediction look like? And I think there are several data sources on this. I've selected the climate action tracker here. I think important to keep in the back of your heads is the graph you saw based on our previous historical trend. But this analysis projects where we would be in terms of global temperature rise by 2100. And if we continue for the next 2 or 3 decades to stagnate and continue to emit at current levels and then start tapering off thereafter, we're close to hitting the 3-degree average rate rise in global temperatures. With an extremely aggressive cut in CO2 emissions up to 50% by the end of this decade, we'd be within the target of a 1.5 degree temperature rise by the end of the decade, by the end of the century, and we need to continue on that trajectory to about 2050 and become net zero by that point in time. So the scale of climate change is a monumental task that faces the entire globe. We've got very limited time to develop technology and get it into production and into deployment. And we really need to change the paradigm of financing large infrastructure projects if we are to tackle this. You know, the conventional way of doing business needs to be revisited. Well, I for one am a proponent of nuclear power, and I certainly believe that it's a realistic option for us to affect this narrative in terms of our carbon emissions. And I'd like to talk to you today about ultra-safe nuclear and our efforts on making an impact to this picture. So as Dave had suggested, we're a privately held US enterprise. We were founded in 2011 and are headquartered out of Seattle in the US. We currently have a staff contingent of over 250 employees around the globe, and we really focus on promoting technology in 3 areas. The first is our micro modular reactor. This is a subclass of high temperature gas reactors. The second is fully ceramic micro encapsulated fuel, which is a patented fuel form that USNC have been developing since inception. And then we have a sister division that looks at advanced systems like space, nuclear power, and propulsion, which I won't touch on in the slides today. So let's talk about traditional nuclear power. And as Dave mentioned, you know, the sort of large grid power plants make up the existing fleet of nuclear reactors. They're typically what's referred to as generation 2 reactors. So these reactors are typically mega in size, you know, above the 700 megawatt capacity in terms of electrical output. They are extremely capital intensive and take a very long time to construct. Recent projects in the US have faced significant cost overruns as well as schedule slippage. So we've really also in the West lost our ability to deploy these reactors because we haven't built many of them within the last 2 to 3 decades. They're fairly complex to operate, and they rely on active safety systems to mitigate potential accident risks and meltdown risks. So you have diesel backup systems and backup systems on those to ensure that in the event of any accident condition, you have mitigated the risk of fuel meltdown. These reactors typically rely on very low levels of enriched uranium, and what that means is that you have a significant volume of high-level waste that these facilities produce during the course of their life. They achieve typically low nuclear fuel burnup and produce a large amount of waste. And because of their design characteristics, they typically operate at a very low temperature range, around the 300 degrees C. I think Coburg is very close to that. It's a pressurized water reactor. And the reason for that is that you maintain water in a liquid state, and you avoid having a phase change within the primary heat. So how are SMRs different to conventional technology? Well, SMRs rely on a different approach to safety, typically looking at passive safety systems, things like gravity, natural convection, and other forms of maintaining a safe plant operation. As David alluded to, the categorization, official categorization of SMRs are at power levels below 300 megawatts. These units are typically, or designers of these units, such as USNC, are taking an approach of a modular factory fabricated unit that can be road transported to the various operational sites. And this really improves the logistics around project management, schedule, and quality management. You've taken all of these activities outside of a site construction environment and basically housed them in a factory. Many of these reactor designs rely on improved fuel characteristics and improved fuel forms. I'll take the group through USNC's fuel form in the coming slides. And really, these passive safety systems allow for simplified operations, and the long-term objective is to actually have autonomous operation of these nuclear reactors. Because of the fuel forms and enrichment levels, the reactors offer a very large window between refueling, and in some cases, reactors can actually be fueled once for life, and no refueling occurs. They achieve high nuclear burnup, producing low amounts of nuclear waste, and many of the high temperature gas reactor designs can achieve temperatures as high as 900 degrees C and even more. So what is the USNC nuclear fuel form? Well, we've based our fuel on the solid foundation of tristructural isotropic fuel, which is known as TRISO. This fuel form has been in development since the 1960s. It's gone through significant amounts of testing in Germany and in the US, and has basically proved its efficacy in radionuclide retention. Effectively, the fuel resides within the center of this particle, and there are various layers, silicon carbide layers and pyrocarbon layers around the fuel. And what these layers do is they act as a mini pressure vessel. So they allow heat to diffuse through the fuel, and they retain the fission product release. So it's a typical fission reaction with U-235, and any radionuclides that are released from the reaction are maintained within the fuel pellet. So really, containment is within the fuel, and no longer sort of reliant on these very large structures around a nuclear reactor to prevent to provide that containment. USNC builds on TRISO fuel. So we take an approach of adding an additional silicon carbide layer in the form of a fuel pellet. The TRISO fuel is loaded into our fuel pellets, and the pellet then provides an additional barrier to fission product release and improves retention capability. To give you an idea of scale, I've got a pencil tip, and it's basically depicted next to a few or a couple of thousand TRISO particles. So these are extremely, extremely small particles. And the rigor and approach to fuel manufacture for these particles is really a significant undertaking. You're manufacturing millions of these TRISO particles, and the quality control that goes into it is actually a significant undertaking. Those TRISO particles are loaded into the FCM pellet, which you can see to the right over here, and then the FCM pellet forms that additional barrier to fission product release. From a proliferation perspective, this fuel form also allows us to negate the risk of having nefarious actors trying to liberate the fuel from this fuel form. So it really provides that additional layer of comfort. In terms of long-term geological storage, obviously these layers would assist in terms of long-term fuel storage as well. So what does the ultra-safe nuclear MMR look like? Well, it's a modest 15 to 45 megawatt thermal design, really 5 to 15 megawatts electrical. It's what's classed as a generation 4 reactor technology. We utilize a graphite moderator and helium as the primary coolant for our. I touched on TRISO and FCM, and our reactor at the 15 megawatt level is capable of a full 20-year plant life operation without refueling. And that has significant benefits to remote locations. You know, many locations around the world are reliant on diesel fuel, and we believe that our 15 megawatt class reactor at first of a kind costs is already competitive in those markets. So in terms of safety features, like I mentioned, there are no requirements for cooling water, electricity, or operator action to keep the reactor safe. And under all accident scenarios which we've evaluated, there are no risks, nuclear safety risks. The fuel never exceeds 1,100 degrees C, and that is well below any melting conditions that TRISO or FCM has been tested under. Our reactor is located below grade, which provides for excellent protection against external impact and external hazards such as airplane impacts and large explosions. And the reactor has what's called a negative fuel reactivity temperature coefficient. So this basically means that as the core heats up, the ability for fission reactions reduces. So we actually reduce reactivity as the temperature of the fuel increases. Is high temperature gas reactor designs a novel design? You know, have these designs been tested before? Is there any precedent? And what we're trying to convey in this slide is really that the HTGR design is built off of a wealth of prototypes and demonstration reactors that have been in place since the 1960s. We have adopted a very conservative approach to the MMR design, not pushing significantly on material temperature limits, as well as taking a very conservative approach to the operating conditions, such as the pressure of the primary circuit and many other aspects of the design. So what's interesting to note is that a lot of the HTGR initial work was done in the West, but really over the last 2 decades, the Far East has been a leader in this area, with the Japanese and Chinese having operational plants as of today. The Chinese deployed their pebble bed modular reactor in 2021, and this is really a sort of world spin-off of the work that South Africa pioneered, and Prof. Nichols was involved with the PBMR project. This has come to fruition in China, and our competitors in this industry are also developing a similar technology in the US. So from a process flow perspective, our reactor is actually quite simple. We have helium flowing through the primary loop. Helium enters at the top of the reactor at 300 degrees C. it flows through the reactor core and gets heated up to 630 degrees C. The helium then circulates through what we call an intermediate heat exchanger, where it transfers heat from that primary circuit through to a secondary circuit. Our secondary circuit is a molten salt loop. And really, this technology has been adopted from concentrated solar power. The molten salt enters the intermediate heat exchanger at 275 degrees C and exits that heat exchanger at 575 degrees C. Then we have a hot and cold salt storage tank. So we've effectively transferred all of the heat from the nuclear reaction into these storage tanks. And the idea behind this is to try and achieve a level of separation between the nuclear portion of the plant and the non-nuclear portion of the plant. The reason for this is that many industrial users, energy users, actually would like to be outside of the restrictions of being a nuclear licensed operator. So we've really tried to structure our design such that we can achieve separation, and we're going through the regulatory process with Canadian Nuclear Safety Commission as well as the NRC at the moment on aspects relating to the separation. So really, in a nutshell, a very simple process in terms of the reactor. I think we have a total of 8 moving parts within the reactor system. To give you a kind of visual representation of what the MMR would look like, we have our nuclear reactors below grade. This is a sort of 2-unit depiction, two 15 megawatt units. These are located below grade, and then we have a modularized nuclear building which supports all of the peripheral and auxiliary requirements for the reactor. We have a sort of secondary control area also located below grade, and the main control room within the container structure that you see to the left of this drawing. On the right side, on the upper side of this drawing, is the energy application portion of the facility. So we have our molten salt storage tanks, as well as conventional steam turbine. There's a set of air-cooled exchanges over here in certain environments where water is not available. Air-cooled condensers are the preferred option. And we basically convert our molten salt into high-pressure steam and run that through a conventional Rankine cycle for power generation. So in terms of our deployment objectives, we currently have 2 projects on the go. The former is our joint venture partnership with Ontario Power Generation Canada. We have engaged with the Canadian Nuclear Safety Commission, what's known as a vendor design review. And this is an early form of engagement, which is pre-licensing, but it gives you the opportunity to engage with the regulator on the technical merits of your design. We've completed phase 1 of the vendor design review, and we're currently in the middle of phase 2. We intend to submit our license application towards the end of this year. That license will be for license to prepare the site as well as construct. We're hoping to achieve the license to construct sometime next year, and then we'll be working towards a license to operate in first power in 2026. We have a second project at the University of Illinois, and that project is to support a research and test reactor deployment in the US. We've started pre-application engagement with the Nuclear Regulatory Commission in the US, and we intend to submit a construction application sometime later this year. We hope to achieve a issued construction permit by the end of 2025, and then we have some aggressive timelines to to get to first power by mid-2026 for that project. So these two projects are really the first of a kind demonstrators for USNC. And through these first of a kind demonstrators, we hope to de-risk the licensing process in both Canada as well as the US, and then be in a position by the end of the decade to be deploying these reactors at scale to support both power generation applications as well as industrial heat. Coming back to that picture on decarbonisation, we've conducted several studies with potential industrial heat users of nuclear power and nuclear energy. I've just pulled out one of those studies. We looked at a potash mine within the Canadian environment, and that facility has various demands. It's got an electricity demand as well as medium and low pressure steam demand. So we looked at deploying the MMRs. This was a 4-unit deployment in that environment, and the graphic to the right basically shows the cost competitiveness from the perspective of levelized cost of process heat. We can see that competing with gas at $3 in MMBTU is quite a challenge for the MMR. Of course, as gas prices go up, we become more competitive. But really the story here, and it links back to the climate change agenda, is there's no current taxation within Canada, although it's on the cards for fossil fuel emissions. So once we introduced a modest carbon tax of $50 a ton, we see that even at the $3 pricing for gas, the MMR is competitive. What's more is that these are first of a kind costs, and we expect the MMR to be reduced to the scale of 30 to 40% as we demonstrate these reactors and gain learning benefits from their deployment. So in terms of other industrial process users, really high temperature gas reactors offer a different opportunity as compared to conventional light water reactors. Because of the higher operating temperatures, we can really support a wider range of applications in industry. There remains some of the holy grail segments of industry which are 1,000-degree plus, cement manufacture, steel manufacturing is pretty high temperature. But we believe that there's a significant market within the 600 and lower temperature range that can be addressed by the MMR. So industry is 21% of global emissions, and a significant contributor to these emissions are actually the direct firing of things like coal and natural gas to support process heat requirements. Like I mentioned in the previous slide, carbon taxation would really make us competitive with today's current costs. So we believe that the next decade holds a lot of promise for this technology, even from an economic perspective. We're designed to, as I've discussed in the sort of process layout, we've really designed this facility and this type of technology to integrate and drop in to existing industrial clients where we can replace the likes of coal and natural gas. And the separation of the nuclear and application is really one of the aspects that we hope to drive and achieve with the regulators. So a final few slides here. I just want to talk about sort of the development of the nuclear industry in general, and I'll start by focusing first on renewables. The graphic to the upper right here basically depicts the supply chain in the solar and wind power equipment export. We can see that the Far East is really a dominant player in this market, with China by far having the lion's share. So, renewables have developed, and the West has been slow to adopt and slow to develop manufacturing capability in this environment. So how does that translate, for the future of nuclear? if we look at the graph at the bottom, these are the number of nuclear reactors commercially operating in the countries listed. And we've seen that in the West, we've had really stagnant demand. In fact, the US have lost some of their commercial nuclear capability over the last 2 to 3 decades. France is relatively stagnant. But if we look at the East, the Russians, South Koreans, Indians, and Chinese have all been really building up their nuclear capability. And I think if the West are to compete in the area of nuclear technology, there's a significant amount of capital required and a significant, let's say, contribution that government will have to take in order to change the narrative and to have the West as a potential technology offering for nuclear capability. So significant public sector funding is required to de-risk these technologies and get them up to demonstration scale. And we need to really push with aggressive innovation to unlock the potential of decarbonizing the world's energy markets. The other aspect is related to the licensing framework. Many proponents of advanced reactor designs have stumbled at the licensing stage, and this is really due to frameworks, licensing frameworks that have been set up for light water reactors. So the technology is new. There's not a significant body of work that can assist the regulators in terms of their approach. So really, regulators need to take a risk-informed approach to these technologies. SMRs hold a significantly lower quantity of nuclear fuel, and their risk profile is really quite different to a large light water reactor deployment. With that, I'll leave you with this final slide on climate change. So I believe certainly that climate change is indeed a choice, and we're at this crossroads now. And I'll leave you with a statement by former US President Barack Obama that we are the first generation to feel the effects of climate change and the last generation who can do something about it. So I urge you all to take up the challenge. And thank you very much for your attention.
Thank you very much indeed. I'm looking at the question thing. I've got a couple of questions myself. In fact, the more I think of, the more questions I generate. So can I start with, I've got three questions. How is the debate with the NRC and the CNSC going in terms of the separation of licensing? In other words, the boundary condition which says the molten salt leaving the plant has no safety impact. How's that going?
Dave, thanks for that. We've in fact been on a working group with EPRI, and we've in the process of finalizing a topical report submission to the NRC on this specific aspect. We've in pre-application engagement, addressed this topic. Certainly, the staffers at the NRC are aware that there are several nuclear vendors taking this approach. And in principle, I think there's some level of acceptance that if we are to really deploy in the industrial setting, then we've got to get this right. And we've certainly received encouragement around this aspect of the strategy.
Okay, I think that to me is one of the really important issues. If we can generate a small plant where, and I almost see a situation where there is a company that runs the nuclear plant under their nuclear license, and the industrial plant next door just gets hot molten salt. So my second question is sort of, you're very close to manufacturing from the look of things. And one of the key issues, and I know this from the PPMR days, is having the industrial manufacturers on board. So how are you doing with industrial manufacturers engaged in producing parts for this and becoming your supply chain? How's that going, and who are you involved?
No, we've made really good progress on the manufacturing and supply chain side. We've got partnerships, in Europe as well as the Far East in terms of setting up the supply chain. There remain certain areas which are tricky. I think with the recent conflict in the Ukraine, fuel supply for many of these reactors has become a big risk area. Our technology is based on the use of HALEU. We've had to relook at our design and look at LEU plus because of availability of HALEU from let's say Western friendly sources, and it pretty much doesn't exist. The US are probably a decade away from commercial production of HALEU. So in terms of supply chain, we've definitely had to look at some areas a bit more closely, but I think in terms of the equipment manufacture, critical components like the helium circulator, control rod drives, those are fairly well under our control. I think the big drivers are probably graphite and fuel.
Okay, I'm just for those in the audience who aren't aware, because you use some wonderful buzzwords there.
I did.
HALEU is high assay low enriched uranium, which is a buzzword for 19.75% enriched uranium, and classical LEU is 5%.
So LEU plus is actually sub 10%.
Sub 10% now. We're moving gently. And the interesting comment is that internationally 20% is accepted as the limit. Above that, you go to high enriched uranium with proliferation concerns. I mean, 20% you can't do much, but above it, once you get 50% enrichment, you can talk about something that'll fizzle. At 80%, you can make a bomb. Ask the Iranians about their enrichment program. So there is a major pressure on the commercial process. Just again, for background, the commercial process for making LEU, that's 5%, is well established in big industrial plants in the West. Almost all the technology coming from Urenco in Europe. But the only people who have kept enrichment plants that function up to 20% is in fact the Russians. Hence the discussion about uranium supply. And just for interest, it's causing us some discussions in Nexa because Safari runs on 19.75% of its uranium, which has historically been sourced from Russia.
Yeah, the geopolitical landscape is quite tricky at the moment.
I'm not even going to discuss them because I'm too close to them. Just tell the questions, and I'm then going to. I've seen no questions on the chat box, so I'm the technology of the heat exchanger. Because that's a big issue in terms of helium. What are you seeing as the technology of the heat exchanger?
So we've been in a development program over the last 3 years with supply of what's known as a printed circuit heat exchanger. So these really high surface area to volume ratio, and it allows us to have a very small heat exchanger located within the underground reactor cavity. We've done some initial testing on this unit, and we believe that it's a much better approach than a conventional sort of shell and tube design, which would require a significant addition of space.
I have to sort of smile gently because that was where with the PBMR, that I'm sure comes from your PBMR friends telling you what to do.
It does.
Because that was what PBMR was building. although it was then helium to helium, not helium to molten salt.
Yeah.
And it is still heat-tricks, or is that, what can't you tell me?
Sorry, Dave, you broke up there. Was there a follow-up question?
Is heat-tricks the supplier there, or are you not? Can you not discuss that?
Yeah, well, you know, I'm probably not at liberty to say who we've been working with,
Okay.
but they've certainly had a significant amount of experience with these sorts of exchanges. Specifically with molten salt, you know, that's part of our test program. There's some nuances to using molten salt. You know, if the temperature gets below a certain level, you have these early crystal formations and solidification. So there's some nuances to managing the molten salt. But as long as you're high enough in temperature, you know, we don't expect any performance issues and risks of rupture on the intermediate heat exchanger.
So just a question, can you allow the molten salt to freeze if you have a shutdown for an extended period?
So look, there's no implication to nuclear safety if the molten salt freezes.
Yeah.
But you certainly could write off your asset. So we have heat tracing systems and backup systems to ensure that we never face that scenario. All of the salt piping is actually sloped to allow for salt return to the storage tanks. You know, once they're in the tanks, you probably have about a week worth of gap before you've got to apply external heating, and you can manage the sort of salt temperature loss by circulating salt between the hot and cold tank. So yes, you know, solidification of the salt is a risk, but it's a risk that's been designed for.
I'm going to okay. Someone's asked. I'm going to get the questions because someone's asked the question of what size of the pebbles and what size of the containers. That's Franz.
So really, you know, the containers are standard ISO containers, so they can be shipped, you know, with conventional trucking and conventional shipping. In terms of the fuel, each pellet is about a centimeter in height and 6 millimeters in diameter.
So it looks a little bit like an LWR fuel pellet.
It does. It does.
And just, I think the question that Franz is asking is, I'm presuming that the pebble, by pebbles do you mean I'm asking Franz the question now, I'm presuming he's talking about the coated particles, and they're about 1 millimeter in diameter when they're completed.
Yeah.
With all the wraps around the outside.
All the layers.
Any discussion of putting this fuel into an LWR? In other words, taking a fuel, a classical fuel rod of an LWR and putting fuel pellets, your fuel pellets in there?
So Dave, actually, you know, that's a great question because actually the foundation and formation of USNC was based on trying to improve fuel form for LWRs. And you know, it's certainly on the cards. I think we've kind of moved the agenda in terms of trying to support our own technology, but definitely FCM and this fuel form could significantly benefit the existing fleet of reactors. It also makes for longer term geological storage benefits, you know, in this fuel form. So we're currently undergoing a fuel qualification program on FCM, and certainly, you know, we aim to use those results to support the nuclear industry as a whole, and not just the MMR technology.
Okay. Okay. I'm going to ask one last question, I still don't see questions on the thing, but it's a fascinating discussion. I can go on for hours on this one because clearly it interests me. You've currently got a maximum salt temperature of 570 degrees centigrade.
Yes.
And clearly some of the industrial applications for process heat. Now 570 is perfect for a steam plant. If you're going to put that into a CSP type steam plant, I'm sure you've specified the temperature based upon that. But my question would be, in a process heat, you might need to have a higher, idealize a higher temperature. What do you reckon is the maximum theoretical temperature you could end up with this, a future variant of this design going to?
So really, we'll have to, the salt has degradation beyond around 620 degrees C. So that's really our limitation on this sort of design, and we'd have to look at alternative heat transfer fluids. But bear in mind, we're trying to license a standard design here, and the 630 is kind of the MMR V1 helium temperature limit. So the driving force for this version of the reactor would be 630 degrees. We do have ambitions to get up to higher temperatures with future versions of an MMR plus or an upgraded MMR. But I think really we're ultra focused as well on trying to get these first deployments off the ground. There's been many initiatives on reactor designs that have turned into paper designs because of looking at too many aspects of the design with low TRL status. So we've really taken an approach here to only adopt TRL levels of 7 and above, and we really want to get the project, we'll get this reactor into the marketplace. Thereafter, we'll be looking at future versions of the design, which could potentially achieve those higher temperatures.
I can't agree with you. I wasn't trying to suggest you change your design, please. I was really asking, where does the concept go to? Because, and you've actually answered the question, that about 620, the molten salt starts breaking. The molten salt you've chosen, which is presumably the same molten salt we're using in the CSP type plant, starts breaking down.
That's correct.
Okay. I'm going to suggest that I'm going to pass back to Minx to close the issue off. Thank you very much indeed, Chirag. I think it's excellent. I'm just so. I got one last question.
Okay.
How do you handle the fact that you're exporting South African IP to the USA? How does that go down?
I think I'll probably leave that to a cold beer someday.
Okay.
I'm probably not the right person to answer it within USNC.
No, I was just going that line because in reality, it's one where the US has a view which says all IP is intrinsically belongs to the USA, and it's a mistake if somebody else has it. And I wonder how that goes down in the US when they say this is basically a South African engineered project, albeit with US money, albeit with US markets.
We've had to jump through a lot of hoops on export control, and it's becoming trickier, in fact. And it's sad to say. I think if we're continuing on the current trajectory, we might have to. Well, there's an initiative to relocate a lot of our staff to the US. So I think that's probably outside the scope of the webinar, but it certainly is a reality.
I just wonder if the South African government has applied the same export constraints to the US, where you could stop the US from using it. But I will not go down that line. That's a rabbit hole and a half. So back to Minx. Thank you, Minx.
Thank you, gentlemen. Chirag, thank you very much for your presentation. Prof. Nichols for hosting the webinar for us. Anybody interested in getting in touch with Chirag and for the presentation, please send an email to webinars with an S at saiee.org.za, and I will forward your email to Chirag, and then he can use his own discretion in sending a PDF of his presentation. Ladies and gentlemen, thank you for joining us this morning. Have a good afternoon further and stay warm. Goodbye.